And okay, so everyone can hear me, and it's okay. So this talk is about fast Python and CPU parallelization. And one of the main motivations about this topic is that probably in the near future, one person will be working with this kind of high performance code, or will be working with someone that knows how to do this. So it's an important topic. And the objectives here is to cover the basics about how can you make a fast Python code and CPU parallelization. And the idea here is that there are three audiences for this. There are the enthusiasts in high performance codes. There are the people that work with that or not, and they like to know how it works, but not necessarily to develop codes. The developers that want to learn how to build these codes and make faster codes, and the ones that just want to know how to run them and don't care about how the things are made. So the talk is more focused in this enthusiast and the developer type of audience. So we start with the early takeaway messages because the presentation is end up getting too big. So I sincerely don't know for how long I will be talking. So I'm gonna let you to decide. So you can tell me when I stop, because maybe this is going to spend more than an hour. So if when you are tired, just tell me that I stop, and maybe we can continue in a second session. So because of that, I will start with an early takeaway messages about how to build, if you want to build a fast run code, what you need to have in mind. First thing, you need to understand what's happening at hardware level and at virtual level. So what it means with hardware level. Basically, you need to understand how the computer is how the hardware computes your code. So basically, you need to know if well, you have a CPU on your PC, and when you run execute a certain code, you are passing information for the CPU to run, or you are passing the information directly to you are passing the information to the run memory, and then this information will be read by the CPU, and then the CPU will execute the code. Or when you run a C or a Fortran algorithm, you are already sending directly the instructions to the CPU. So what's happening? Because you need to understand that the computer is based in physical things and in transistors and wires. So the information takes time to dislocate from one part of the computer to the another. So if you want to really do fast codes, you need to understand when you execute a code, what part of the computer is being accessed and which other parts it will have to communicate. And what I mean then at a virtual level too, and then virtual level here, it's the virtual expression here is an abstract meaning to convey the idea of the interaction in software to hardware level, because a lot of the codes and software that you will run on your PC will have auxiliary programs to help it to communicate with the hardware. So you don't need only to understand the hardware level, but also how your softwares are communicating each other so that you can access the computer. And the other reason that I'm using this word virtual here, it's about the second suggestion that I use here. That is, find out what you need to find out what each specific term that you are studying means and its origin. And this is what I call thinking in English. What I mean with that, for example, if you take in Portuguese, I don't know how this is in Spanish. Sorry, área de trabalho. So the desktop in Portuguese, we say área de trabalho. So the translation will be work area. And so if I ask my nephew, Arthur, o que é a área de trabalho? What is the área de trabalho in the PC? He will think a little bit and say, well, it's the place where I do, it's an area where I can work. And he will be right about that. But then you could ask him, so why it's called desktop? And maybe he will kind of don't know the answer about it. And if you think about the reason why it's called a desktop, so the origin of this word is comes back to the Xerox labs in the 70s, if I'm not wrong, where they started using this metaphor desktop. So the idea is that the interactive user interface that appears on the screen resemble a real desktop. And if you notice, when you are working in a desktop, you have a limited space. And if you are with a lot of articles on top of the desk, and you pass one article in front of the other, you cannot see what's under the article. So they take this kind of experience that the humans had for centuries of working with desktops and place it in the computer. This is probably one of the main reasons why this desktop metaphor is so it was so successful, and we use it until today. So this is just an example to show the importance of when you are thinking, when you're studying things on a computer, you need to think them in English. The English words are ways to convey meaning, and in the English, in English, they create a lot of words through concatenation, and basically all the words in computer science are made in English. So it's very good that you think in that language when you are thinking about computers, because then it's much easier to understand certain things. For example, if you think in English about lareira, in Portuguese, the fireplace, it's actually just to take the word fire and the word place and concatenate, then you have a fireplace. So it's much easier then to understand what fireplace means if you can break this word in this small pieces. So this is I think it's a very important way of thinking. And for example, when you have a hard drive, so HD or HD, so you someone may think, okay, it's a hard drive. So if it's a hard drive, then maybe it's a hardware. So it means that hard drives are hardware, and so so it means that the RAM memory is not a hardware, or what's going on. And if the person goes back to see what's the origin of the word hard drive, hard disk, it will be actually that on the past, the first hard drives that you store memory, they were literally a drive that was hard. So when two people were talking about saying, "Oh, pass me that drive," the other researcher would ask, "Which one?" They would say, "The hard one," and then we started using the word hard drive. So knowing the origins of the
Paulo, um pouquinho mais de objetividade, por favor.
Okay, sorry. Then Google the heck out of it. So just that. So the expression you need to use Google a lot. So if you want to learn something about programming, use the Google a lot. And I like to think about that in the way that is learn about what you want to learn before learning what you want. So what that it means that is actually is that before, if you want to learn something, before you go into those YouTube tutorials with 3 hours long explaining everything about a certain language, you need in already trying to learn that thing, try it before to learn about the thing and the context of that, and then you try to learn how to use it. So my personal algorithm that I use is I first look at YouTube videos, then Wikipedia entries that helps a lot to see the meaning of the words and the origins of the words, then specific blogs, and just then, when I already understood what I'm going to learn, then I go to tutorials and forums, and spanning all this learning process, you have the official documentation. So the official documentation should be the first place where you look. And the problem with official documentation is that they are written in a very specific language. But once you understand how the official documentation is written and how the language works, this is the best place to use because it will be the most concise one. Okay, so and then about the forums, basically 2 types of forums. They are like Stack Overflow that I use a lot, where you have it's more a soft forum, so you have a lot of beginner questions and sometimes a lot of things going wrong there. But if you see 10 carries about the same question, you can take some good knowledge about it. And then the Type B forums, they're more hardcore, like this Google group, this specifically about F2py and Cython. And what you see sometimes in these types of forums like Stack Overflow is if people being very arrogant and teaching things wrong. So comes to the other topic that about computers is to be humble and embrace the rabbit hole. So computer is very there's a lot of things in computer, and you just need to embrace the complexity of it and do not try to understand everything, and understand that we will always have someone that knows something you don't know, and we always will have someone that don't know something you know. For example, in this group, in this forum that I showed, the groups, someone was asking what is the best what's the best language and method and hardware architecture to resolve 2D Laplacian equation. And one of the people, this guy on the group, he answered telling that you cannot get a best performance just by separately thinking about good compilers or optimizing memory access, specific programming language, certain hardware. To get the best performance is more an holistic experience where all the above elements count. So it's a complicated thing, and this is what I mean with embrace the rabbit hole. You need to take things slowly. And so he says also that questions like which is the best compiler, or which is the best platform are no sense, and you should ask, I have this problem, which technique or tool should I use so as to solve it optimally? So then he also said that testing language on benchmark, it's always something that it's not totally secure, because you basically for each task you may have a better language than the other. And the final thing is the what I call the fractal abstraction technique. So I like to use this term, but this is an idea that I learned in the YouTube videos, where you need to understand that in computers it's always kind of this fractal tendency. So if you think about the basics are transistors, and so you don't really need to know how transistors work. You need to know that transistors are something that makes you let you go one way or the other. Then if you take like 3 to 6 transistors and put them together in a certain specific way, you can have logical gates. And then if you join these logical gates in another way, you can have something that can save or decode 1 bit of information. Then you don't think about these complicated transistors and logical gates anymore. You just put like a square box around it, and you create a level of abstraction, and then you have something that decodes 1 bit. Then if you want to have a byte, that's 8 bits, you place 8 of this abstraction box side by side, and you have 1 byte. Then if you want to have 1 megabyte, 1 million of that, you set another level of abstraction, and then you have 1 million of those 1 byte boxes. And then you go raising and raising this fractal level until you have your PC. So this is the basic takeaway message. And so, results. What's the idea here? The idea is that Python is slow, and we want Python to be fast. So if you go on blogs, basically this is a basic notion that people will have. So you have on the right side you have the language and their speeds, and on the right side you have a CPU execution mode to be serial or parallel, and also you have a third option there would be GPU, but we are not talking about that, so let's take that aside. So on the language, basically what people understand is that Python is slow, and then you have C, C++, and Fortran. They are fast, and basically they are debates where they are equally in the same order of magnitude. And then we have this newer interface, like 10 years from now, which are Numba, Cython, and F2py. And what are these 3 things here? They are what's called wrappers. So, and wrappers, what are? They are ways to inside wrappers for Python. So inside of the Python code, you can use these wrappers so that a specific function on Python be as fast as a C or a Fortran. But okay, so and generally when we are talking about on blogs on those things about parallelization, you have Python libraries that can do parallel process, and you have OpenMP that can do parallel threading. So basically, this is what people start to question and then start to asking. So what's faster? C is faster than Fortran, Numba is faster than Python, Cython is faster than C. Can I connect Python libraries with Fortran? Can I use OpenMP in F2py? What's OpenMP? OpenMP it's a language. What is Numba? So it starts a lot of confusions, and the best way to approach this is to use a level of abstraction. So abstraction is not only to make the things simple. Abstraction is to make the things more generic so you can work off them. So, for example, when you are going in the bathroom, you don't have a very detailed photo of a person there. You have an abstraction of a person because it could be confusing to have a bathroom to a very specific face of a person. No, you want something more abstract. So instead of thinking about all the language, you need to think on the abstract level of them. And so this is basically what the problem in question. You have the language here, so you have the compiled language, they are the faster ones. You have the slower one, the interpreted one, and then intermediate, you have the interpreted one that are rapid with compiled functions. And basically the difference in speed is because when the computer at hardware level, at the processor, the computer works in machine code. He works with bytes. It's zero sequence of instructions in bytes, 0 or 1s. But when we are writing code, we are writing in program language, which is called a source code. So the way that you go from source code to machine code is through a compile, and a compile it's a way to tell the machine how to run our source code. And as fast, the most fast code is the one that can tell the machine to do a same task with the minimal numbers of machine code instructions. And these are basically the compiled language. And what this interpreted language do is kind of they instead of passing the source code directly to the machine code, they have an intermediate step where they run their code in a virtual machine, where you have like 100 more, 30 more steps to do the same thing. And why we use interpreted language if they are slow? Because they are more easily to adapt and more easily to program. That's why it increases. So basically, this is the difference. And then we have this interpreted rapid compiled functions, where you can use an interpreted language like Python that is easier to code, and then wrap only just a bit of the code with this wrapper, which can be a decorator. It is basically a flag that when the interpreted is running and get this flag, this flag will tell the interpreter that he needs to call a compiler, and then the compiler will get only this piece of the source code and pass it to machine code. And then you have a virtual but with a lower level working in the machine code. So this is the difference. And when we are talking about CPU execution, generally people know that if you have a serial, it's slower, and if you have parallel, it's faster. But that can change. And one of the first confusion is about what's a concurrent execution and what's a parallel execution. So the term concurrent, it means that you are doing in the same time frame, but not at the same moment. So, for example, if you are playing a video game on the computer, and then your boyfriend or your girlfriend ask you to go to the kitchen and taste the food to see if it's good. Then you are playing and you run to the kitchen, taste, and then came back. You keep on playing. This is a concurrent execution because you are in the same time frame playing the game and tasting the food. A serial execution would be you are playing the game, your boyfriend, girlfriend ask you to taste the food, and you simply keep playing and you just taste the food after you play it. And a parallel execution will be you are playing the game and at the same time you are tasting the food. This will be parallel. So this is the difference. And in this 6 quadrants here, it's basically everything that you need for the basic knowledge, so you can navigate through this massive, very massive world of blogs about fast codes and computer science. And then here you can, in this level of abstraction, you can start to think, okay, so like maybe I can get the interpreted language to be concurrent or parallel or compiled and serial. How can I connect all those things? And after that, now let's bring back the language. And basically, so we have the Python, which is the interpreted language, and then we have this option for Python, Numba. What is Numba? Numba is a wrapper where when you write a code, it's a wrapper that works as a decorator. So you're writing a Python code inside a F2py algorithm, and you define a function in Python. Then what is Numba? You simply write one line above this function, and this works like a decorator. And when the interpreter is running the source code, when it gets to this line, he would tell to the view LLC compiler engine to compile this function in a C using C or C++ engine, and then you have a very, very, very fast Python function running in your code. What is Cython? Cython is a way that you and Cython and F2py are two similar things where you write a Cython external model, so a C external model or a Fortran external model, and then you compile it using this NumPy library that allows you to do this. You compile this external model files in C or Fortran into Python functions, and then your Python main code can load these functions. And when these functions are called, the Python interpreter knows that these functions have to be treated as compiled ones, and they have to be sent directly to the machine as a machine code instruction. So they can be as fast as C or Fortran. And then you have what you already know as C, C++, Fortran, they're very fast. And in the side of execution, basically we have the concurrent, like I put the C here, and in parallel LP. So we have concurrency multi-threading, and we have in parallel you have multi-processing and multi-threading. So you see that you can have multi-threading parallel and multi-threading concurrency. And this is one of the reasons that people get confused and don't understand what is happening. Right now I will not enter on this, but basically when we are talking about this language, these are the tools that we can use for each thing. So Python has a concurrency model which is called threading, that have the class thread, or you can do concurrency threading in Python, and but concurrency is not parallel. Concurrency is it's waits not to waste time, right? So and parallel, then we have for parallel threading, we have OpenMP, and you have others like it. Is the core? It's directive. So it's what she calls application application program interface. So it's something similar to Numba, you apply to C or Fortran or C++, that basically you have directives that you put on top of loops in Fortran or C that will tell the compiler when you reach this directive or pragmatic, basically what this directive is telling to the compiler is that, well, once you get to this directive, the loop that is below it, it has to be parallelized in the way the directive is telling to do it. So OpenMP is not a language for program language like CUDA. OpenMP is just a directive that you put inside C or Fortran code. Then you have also Numba parallel threading techniques that they are basically using directives like OpenMP. And then you have the parallel processing options like Python process. And then another thing that you need to fix in this board is that basically Numba, Cython, F2py, C, C++, and Fortran, they are all fast equivalent, and they are 10 to 1,000 times faster than Python. So they will be about. It's hard to be 1,000 times faster than Python, but if you write a very bad Python and if you write an excellent one of those, maybe you can achieve something like that. But basically, they will be to 20 to 70 times to 300 times faster than Python, and they are basically all have all the same efficiency. So if you search a lot of blogs, you have different entries showing different results, but they are basically equivalent. So what are these colors here? Basically, because as dark as it gets, the color, more liberty and more control of what's happening you have. So Numba, it's ridiculously easy. There's no reason why we shouldn't try to use Numba, because you don't need to change almost nothing about your code. You just need to place one line decorator above your function, and and if you want to have a parallel process like Numba OpenMP, you just need to put an extra argument on this line, and then you have a code that run as fast as C or Fortran in that part of the code. But you cannot tell much instructions to Numba. So the Numba wrapper has to find out how to compile the things you are passing. When you are working with the Cython and F2py, then you have more control, because you are actually explicitly writing functions in C and functions in F2py, and then you can use OpenMP modules to have more control of the parallelization. And they will be as fast as C as Fortran as well. But you will have a little less control than if you only use it a pure C or a pure Fortran. But so this is the difference, and you have this gap here. And of course that you have to be fair with Python, because Numba, Cython, and F2py, they are Python based instructions. So Cython is not a programming language, and Numba is not a programming language, and F2py it's also not a programming language. So let's show you some results of loop optimization with F2py. So now I'm going to show you 4 codes, a Python code, a Numba Python, a Cython and F2py code, and the times it took to run from this guy here on Stack Exchange. So starting with Python. So here you see they are doing a basic Python definition of function. The name of the function is Python, and what it's doing here is doing for loops, for loops. So 1, 2, 3, 4 loops, and it's adding each element of this 4-dimensional array or matrix and returning the element B. So you define this function, And in the main program, you import NumPy, for example. Then here he's just initiating a random, a random matrix, and then he passes to the function as I normally do. Then he can print and everything, and then he measures the time. And I will show the time after showing all the methods. So look what's happened when you try Numba. You see the difference? The only difference is you have to, from Numba, import JIT. What's JIT? JIT is this class of decorators from Numba that means just in time. The just in time decorators, they appear first time in Java, but then they were propagated to other languages because they allow you to do this wrapper around this function and compile it so it can go direct to machine code and be very fast. So the only thing you have to do here is add this one line, and here specifically he is defining the matrix here. So this is an argument that syntax, but it's basic. And you say non-Python equals to true. It is basically saying do not use nothing about Python when you do this wrapper, because I want you to only use C and C++ engines. And that's it. You see that the way he's calling the function is exactly the same. So, and then you have something working very, very fast. Very, very fast. Okay. So now what is Cython? Well, now Cython actually it's what's called a superset for Python. So it's not its own program language, but it's not C written. The idea of the Cython is that you write .pyx program where you have your Cython model function subrouting. And the nice thing about Cython, and one of the reasons why it probably is the best option of all those, is that you literally write it as a Python code. If you see the syntax, it's exactly the same. It's exactly the same of Python. So you write in Python. So you are doing a C fast thing that you can write in Python. And the only thing that you need to use here is the classical kind of C definition. So you have a C definitions, double B. So you have a float B, you have an integer EJL, and when you are defining a function in C, you need to declare what is the type of the function during the definition. So the only thing that you have of C here is that you need to do these definitions, and then look how it's easy for the Python code to run it. So basically you use this, there's more than one library that you can use to compile. Here they're using the term install the Cython module. And like there's several ways that you can compile. You have different compilers for C, for that. And here he's using pyx import, and pyx import has this method called install, where you need to Google the arguments, but they are not that hard. And when you run it, this call it's already compiling the function, and then you can import directly by using the name of the function, Cython, and then use it just like if it was the simple Python function. And then you have a totally C function running inside of your Python, and you wrote it in Python. So when you're talking about Numba Cython, there's probably no reason why you shouldn't try this, because it's there. You know, if you know Python, you can use this. So why not? And then you have the F2py. So F2py, then you need to really indeed write a Fortran file. So, but instead of doing the natural begin program, end program statement, you need to use a subroutine statement. And a subroutine written in Python, in Fortran. When you compile, use this F2py compile. It's a NumPy tool to compile an Fortran subroutine into a Python module. Then, when you compile this subroutine, what's happening? You have the program in Fortran, subroutine. Then you run the compile. Then the compile, we use this NumPy and C built-in libraries to convert this source code into a C-like structure, and then to pass the C-like structure to a module in Python that will be directly connected to machine code. So it will be Fortran fast. And then to use it is the same thing as the other ones. So here I'm importing the Fortran run. So because Fortran run is the name, the output name I set for this module. And inside this Fortran run, it's basically the module version of this program, you can have several functions or subroutines. So I'm using the basically Python syntax. So it's for the module dot, the name of the function, and then you load the function, and that's it. You have an F2py code. The F2py is probably the most tricky one because you have to know some specific things. For example, when you are declaring a subroutine here, you have A and B, and so B is what you're going to return. So instead of writing a return like in C or in Python, you declare it inside of the subroutine as an intent out, and the A as intent in. And when you call the Fortran module here, you see that you are not passing two arguments. So M would be A here, and B would be the output that you want, the sum of M. So C. So you don't have to pass these arguments because the wrapper that is connecting the Python to the F2py module, to Fortran module, knows that the output that you set here will be the second argument. So if you place the second argument here, the code will just not run. So most probably Cython 2 has these peculiarities, but as I understood, first F2py is the one that have more peculiarities. So basically that's it. And when you run these 4 types of codes, what you find here is that Python takes like 22 seconds, and then Cython and Numba are what is this? 200 times faster? Is that's it? I think that's it. And in this case, F2py is very, very much lower than Cython and Numba. So if you take this result as an absolute result and say, oh, okay, I will not use F2py because F2py is complicated and is 20 times slower. But the problem here is that when this dude was applying this F2py structure, he didn't not know about what is called column measure or row measure. So it's related to the way that the Fortran compiler and the C compiler translate the source code to machine code and how this will be allocated on the memory. So when you have a multi-dimensional arrays in Fortran, Fortran will store. Now for example, Fortran will store because the memory is a unidimensional. Memory is unidimensional. So if you have a multidimensional structure, you need to break it as a unidimensional thing. So you can, so basically you can write on the memory? Well, on this multidimensional array, I will write first the columns, one each after the other, or you can write the rows one after each other. And Python and C work differently. So in this case, his Fortran code is performing 20 times worse, because he is using for all these codes what is called the C, not C major, C continuously. I don't know how to say this word, but basically it's using wrapping the F2py function as it was going to follow a C structure, and then the F2py gets very, very slower. But after that, he fixes it, and the velocities are the same. And back in that blog about that I showed before, where they were trying to solve a 2D Laplace equation using several methods. So here you have a different result, for example. Here they are comparing Fortran, vectorizers, C, Cython, NumPy, Cython, and here, for example, the guy that was asking about this was because he found out in the internet that the same code that he was running in Cython, there was another guy running in F2py, and in F2py was 6 times faster than in Cython, so he was very worried and asked, well, maybe should I change all my codes to F2py because F2py is faster? And then this Rajev here made a lot of benchmarks and showed that no, it's not like that, because you can see here, for example, that my what is this? Oh, okay. So in this situation here, he have actually F2py faster than Cython, but it depends, because here in the run 8 here you can see that the Cython vectorized is running at the same speed as Fortran. So you are seeing a lot of names and a lot of different things. You have a parallel update, non-parallel update, basically to say that it's not, when you are running a Cython, Numba, F2py, C, C++, Fortran, that there is not a fast, the one that's fast. All of them are fast, and if you code it right, they will be fast. So you don't have actually to be worried about which one to choose. Basically, you need to choose the one you will be more worthy for the moment. For example, if you are running a Python code and you just want to hit the push Python code that go faster, use Numba, because it just plays one thing and the code will be very, very fast, and you can even parallelize it after. And if not, well, try Cython, because it's basically Python, but you write in a different file and use 3 lines of import to make it run. And another thing is that to make it more complicated, indeed, NumPy has this function here called ensum. This method from NumPy is specific for you can work with matrix. So when you compare this NumPy engine with Cython, with Numba, with F2py, and all those other things, even with C and Fortran, you can get like 6 to 20 times better performance than Cython, than C, using a NumPy thing. And what's the message here is that it's not about how the language is written, if the language is fast or it's a good language or not. It's more about how good is the compiler that will treat this language, because you can write a very bad language with a lot of messy source code that you need several machine commands to make it run, but then you can always run a very good compiler. That's this let's say software that make the life software when you try to connect to the hardware, and reorganize this shitty code in something very, 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 very fast. And basically, this is what things like this does, and actually things like Numba does, things like Fortran does, all the O3, capital O3 optimizations. So the basic idea here is that what will determine if the language is fast, which we stand a lot in the fields of the compiler and how the compiler is communicating with your hardware and hardware to software level. And here this video is very nice if you want to find out how to computer read code frame of essence. It's very, very nice. It's funny. And it's basically explained that you have the source code, and then you have this black box, the compiler, and then you have the machine code. So let's talk about that. And if you are an enthusiast of new languages and stuff, and you really want to taste something that is quite new, you have Julia. So Julia, maybe it's like the new Python or something like that. But what's nice of Julia is that it's a proposal language like Python, but it is fast. It runs fast as C, as Fortran, as C#, and in this, if you like to look to benchmarks, there's the computer language benchmark game where you enter in this web page and you can test several languages against Julia in this benchmark game, and you can see that Julia can beat Java. In Java things can beat Fortran. In Fortran things can beat C. In C things, and it also lose for those languages in several scenarios as well. But Julia, it's a very interesting. So if you are an enthusiast of new language, this could be very, very good one, because it's so it's not like it's a Python that they are modifying. No, it's its own language, and it's totally inspired in Python and that stuff. But it's its own language, and the idea of this language is to be like as beautiful as Python, but as fast as Fortran and C. So this is about language. So I guess that this is gives the message about the language. So the second part would be, so now let's talk about CPU execution. And now I will ask about the time, how we are. If you want to stop here, if you want to continue, and so give me a feedback, please.
Paulo, eu acho que já foram 53 minutos. Então, em geral, a atenção já era. Eu acho que tu podia abrir para perguntas e depois continuar na próxima quarta.
Okay. So this was the part one of the talk. So about the language, and the part two would be about execution. So I will show some results. I will explain how each one of those things works and are, what is a core, what is a thread, what is a parallel processing, what's a parallel threading, and how to make the best use of these tools here, combining with the language. And given in the end of the next week, I will show my preferred way to work this in. And have the optimization of our routine. So that's it for now, and it's open for questions. And thank you very much for listening to me. And sorry if it was too slow or something like that.
I have a question, if no one else has. So for me, it's not clear the concept of concurrence you mentioned. You gave some examples, but it was not clear for me.
Yeah, so it would be more clear in the second part. I will jump some slides to go to the right here. So this image is interesting. So what we could see here is that you can have in this parallelism scenario, you have two threads that
parallel is clear, but I cannot see from this this sketch what is the difference between concurrence and serial.
Okay, so so this concurrency is what happens here in this gray area called Python threading tools. So these concurrency tasks, they make more sense. Actually, they only make sense in scenarios where you are having processes that running some machine instructions that end up in the input-output scenario. So, for example, imagine that you pass a sequence of machine instruction to the CPU, and you have only one CPU and only one thread only one thread of execution.
Pode falar em português que não tem mais ninguém, não tem mais nenhum hispano aí.
Todo mundo caiu fora. Bom,
não.
Parece que não foi boa a apresentação.
Não, só os hispanos caíram fora. O pessoal continua aí.
Eu tô ouvindo aqui, Paulo. Só pode falar aí.
Tá. Então é assim. Imagina que tu tem eu vim pro português e esqueci as palavras. O que eu tinha falado? Tu tem uma sequência de instruções em código de máquina que tu vai passar para o processador. E tu só tem um processador e tu só tem uma via para passar essas informações. Né? E daí isso seria um single core com um single thread só. Porque só tem um thread de execução, ou seja, só tem um fio de execução. Aí, esse código que tu passou, ele manda fazer um monte de cálculos, e daí quando chega em algum momento, ele diz, ele diz, print na tela o resultado e espere pela resposta do operador. Esse espere pela resposta do operador é um momento que a CPU está no estado de input-output, ou seja, onde ela fez um input, fez um output, está esperando um input de volta. E o código, e essas instruções que você passou para a máquina diz que o processador ele tem que parar até que a resposta venha, porque ele precisa da resposta para continuar calculando, né? Só que daí, imagina que isso é um programa, só que daí tem um outro programa vindo atrás, né? Que quer rodar depois que esse programa terminar. Só que esse programa ele está esperando a resposta do usuário. Então, até o usuário não responder, se ele demorar muito, sei lá, por exemplo, o cara mandou rodar e foi no banheiro. E daí o processador vai ficar em idle, ele vai ficar parado esse tempo. E esse tempo que ele está perdido parado é o que tu consegue ganhar com concurrency. Então, como que é a técnica que tu faz? Na CPU, tu vai ter os registers e os cachês lá, que são memórias super próximas da CPU e que são bem caras e que são pequenas, mas são super rápidas. Então, o que essa técnica faz para fazer essa concurrency? Em vez de dizer para o processador ficar tipo parado até o cara devolver a informação, já que ele está demorando, quando chega nesse momento de parar e tem um outro código para andar, ele pega e joga esse código que está parado para um desses registradores, dessas memórias dentro da CPU, e com um flag que isso aí só tem que voltar para o thread ali principal depois que o próximo código passar, ou depois que o cara voltar do banheiro. E assim, enquanto o cara está no banheiro, o código que está atrás pode ir rodando. Né?
Vocês
Então,
querem uma ajuda dos universitários?
Por favor.
Tá. Então, a ideia é a seguinte. Eu tenho uma máquina de lavar e uma máquina de secar. E isso é um processador. Aí eu posso lavar a máquina, eu posso lavar a roupa e depois botar a roupa para secar. E aí eu pego a roupa seca e tá pronta, tá? E
certo.
isso é processar uma operação. Se eu tenho cereal, eu pego a roupa, lavo, seco e devolvo. Eu lavo, eu seco e eu devolvo. Só que toda vez que eu faço isso, uma das duas máquinas está parada sem fazer nada. A ideia da concorrência é assim, eu pego a roupa de um cliente, eu lavo e boto para secar. E no que eu botei para secar, eu já pego a roupa de outro cliente, ou seja, eu posso pegar processo...
Mas aí tu tem duas máquinas, é diferente.
Não, porque o processador ele é feito de várias partes. Ele tem a parte...
então não é só uma CPU.
Não, é uma CPU só. Porque a CPU é feita de uma máquina de lavar e uma máquina de secar.
E qual é bom, aí a gente precisaria de um desenho da CPU.
Tipo, tu coloca funções para os threads, é isso, Karine?
É que assim, o Paulo, quando ele tentou explicar essa ideia, tem toda a ideia de pipeline dentro do processador que foi pulada. E o que acontece? O pipeline ele funciona assim, o teu processador ele não executa uma instrução de cada vez, mesmo um processador. Porque cada instrução ela tem várias partes. Primeiro tu tem que descobrir qual o endereço que está as tuas variáveis. E aí tu tem que buscar essas variáveis. E isso é a primeira parte, é lavar a roupa. A segunda parte é fazer a operação efetivamente feita. E isso já está em outro pedaço do processador, que é a parte realmente da CPU, que é a halo. Depois da halo, ele vai para a parte, de novo, de escrita. Porque tu tem que guardar todo o resultado de volta na memória, no disco, onde quer que esteja o dado. Então, a ideia da concorrência é que tu pode usar essas partes diferentes do processador, não necessariamente para o mesmo processo. Então, um processador só, fazendo coisas diferentes ao mesmo tempo, porque tu tem pedaços diferentes dele.
Tá, e quando tu faz threading, é essa separação que está envolvida? Ou tu efetivamente tem duas estruturas desse tipo aí que tu descreveste em paralelo dentro de uma CPU?
Então, esse é o ponto. Depende, porque tem processadores que diz que é multithread, quer dizer que eles fazem concorrência dentro de uma CPU só. Quando é multicore, aí tu tem que ter várias máquinas de lavar e várias máquinas de secar ao mesmo tempo. Aí são hardware separados.
Não, mas aí é multicore. Eu quero saber se o multithreading é com uma CPU só e com esse trabalho...
Eu posso mostrar os slides que eu iria explicar isso, se tu quiser saber. Mas...
Não, tá tranquilo. Acho que pode falar da outra vez. Era só... que não estava claro para mim o que era.
É que o Paulo fala muitas palavras para explicar uma ideia.
Eu falo bastante.
Aí eu me perco rápido.
Então, Paulo, então, com relação ao seminário, acho que aquela introdução lá tua, que seria para o Bernardo, por exemplo...
Acho que a gente pode parar de gravar.
É.
Sim.
Isso.